Hey kiddos, good to see you again. Happy lesson number 8. We're counting down to lesson number 10, so it's close to the end. Let's take a look at what our goals are for today. Alright, so today we're going to debrief that electric field strength simulation and define some relationships for electric field, specifically electric field due to point charges and electric fields due to parallel plates. And then we'll introduce electric potential and electric potential difference, which you may have heard of called voltage. All right, let's go ahead and get started. All right, so here's a quick warm-up. After I get done reading the question, I will ask you to pause the video and give it a try. I will present a similar problem having to do with electric fields later on in this lesson. So for the warm-up, we've got 2 point charges that are sitting on a ruler. A point charge, Q1, has 8.5 microcoulombs of charge and is sitting at the 3 centimeter mark right here. Another point charge, Q2, has a charge of negative 21 microcoulombs and it sits at the 9 centimeter mark. Find the magnitude and direction of the net force experienced just by Q1. The net force experienced by Q1 is what we're looking for. As a note, microcoulombs is the SI abbreviation for times 10 to the minus 6 coulombs. All right, please pause the video and give this problem a try. All right, let's see how you did. So a couple of things that I want to point out conceptually is that since the 2 charges have opposite signs, they will be attracted, right? Those forces will be attractive. Also note that between those 2 forces, or between those 2 charges, the forces are equal and opposite. So no matter whether I asked you, because actually there are only 2 charges interacting here, no matter which charge that I asked you to solve for, you would get the same magnitude for the force. Okay, so we're looking at Q1, right? Q1 is positive, Q2 is negative, so they're attracting each other, and the attractive forces are equal and opposite. Q1 will feel a force to the right, okay, towards Q2. Couple of things to note when you're doing this calculation is that the charges need to be written in coulombs, not microcoulombs. Right, so it would be 8.5 times 10 to the minus 6 coulombs and negative 21 times 10 to the minus 6. And R is the distance that they're separated in meters. So between the 3 centimeter mark and the 9 centimeter mark is 6 centimeters. You're going to write 6 centimeters in meters when inputting these into the equation. So your answer would be 446. You might round to 450. And that force is acting towards Q2. All right, so let's take a look at our electric field simulation that you completed, and we're going to do a little debrief. Okay, so electric field lines are drawn in the direction of. Okay, so in the simulation, if you turned on the electric field lines, were there any patterns that you noticed? What you should have noticed is that the electric field lines are drawn in the direction of, or the direction that, a positive charge would be forced in that region. Okay, So the electric field lines are always pointed by convention in the direction that a positive charge would be forced. Okay, if we put a negative charge in a region, it would be forced in a direction opposite to the direction the electric field is pointing. Okay, then as we get further away from a charge, as the distance away from the charge increases, the electric field strength should decrease. Okay, and I asked you to make a graph to show this relationship explicitly. And this is a graph that I literally pulled off of a student's assignment. And so you would have seen that electric field strength and distance are related in an inverse squared relationship. So this person got electric field strength equals 8.8 over distance squared. Is that consistent with the equation that we've got for electric field strength? Yeah, and we could go through the process of figuring out the value of the charge that was being interacted with, but an inverse squared relationship is consistent with what we've talked about in the past because we've used electric field strength is equal to K times Q over R squared. Okay. So as the electric field strength, as the distance away from a charge increases, the electric field strength decreases. All right, and then one more relationship that I asked you to graph. As the amount of charge increases, the electric field strength increases proportionally. Okay, so this person got electric field strength equals 9.07 times charge. Okay. According to our relationship that was up here, what would that 9.07 represent? Well, electric field strength equals K times Q over R squared, right? So here we can see that the electric field strength and charge are directly proportional. Here the constant would be Coulomb's constant over R squared, is what it should be. Okay. Yep. Sounds good. So that makes sense based on any background information we had. And I was asking you to complete this simulation because it's so important to have a conceptual sense of what electric field strength is, what direction it points, how it changes as charge changes or distance changes. Okay, for our understanding of electricity and circuits that will start at the beginning of next year. Okay, now I did some pre-drawing on this slide just to kind of help us out with some time. But again, we had done some comparison a couple weeks before, previously of electric field strength and gravitational field strength, and what you'll see are the equations that we had in our graphic organizer that we developed a couple of weeks ago. All right, so gravitational field strength conceptually is gravitational force over mass. Electric field strength conceptually is electrostatic force over charge. And then we have specific equations that we can use to do those calculations. Okay, and one of the things that we can do is draw those electric field lines that are in the simulation. Remember, electric field lines were drawn in the direction that a positive charge would travel in the region. Okay, so electric field lines are drawn. An attempt is made for them to be evenly spaced around a central point charge. Here I labeled my central point charge Q, and I labeled it as positive. And because that central charge is positive, I know that if I place any small positive test charge out here, it would travel away. That positive charge would travel away from this big positive charge. So that's the direction our electric field lines are pointing. Okay, so typically, here, let me redraw this. When we are testing the direction an electric field is should be drawn, we want to imagine that there is a tiny positive test charge, and we label that as Q naught. A test charge is typically positive, labeled Q naught. I tend to put a little plus sign just as a reminder. Test charge. Okay, and when we're trying to figure out the direction that the electric field should be drawn in a region, I want you to imagine that there is a tiny positive charge, and imagine what direction that charge would go in that region. And anywhere in this region around this big positive charge, our tiny positive test charge would be repelled outward. I also want you to look at the density of the electric field lines. Density tends to represent electric field strength. So here, closer to the charge, your electric field lines are closer together, which means the electric field strength is stronger, closer to this big charge. Out here, the electric field lines are further apart, which is by convention, it says symbolizes that the electric field is weaker further out. We could also say, what if we doubled this charge? How would we change the electric field lines there? Well, if we doubled the charge, we'd have to double the number of electric field lines. And again, an effort, not a great effort, but a little bit of effort is made to make those electric field lines fairly uniform. Okay. Similarly, what if, similarly with the gravitational field strength, if gravity can only ever pull things inward. So if we had a little point mass, a test mass, we'll think about the direction that gravity would pull. It's always inward. If we doubled the mass, we would double the number of field lines, showing twice the electric field strength, twice the force. And you'll notice that for both of these, I draw the arrow indicating the direction of the electric field in the center of the line, because it would be very inconvenient to draw all of the arrows at the surface of this mass here. They would get kind of all bunched up and they would be difficult to see. So I just, as a habit, draw them in the center. Okay. So the arrow and thus the direction is easier to see. Now, here's a note that I made here. Electric field lines are drawn by convention in the direction a positive test charge would be forced. And so if we had a negative charge that was creating an electric field, you want to draw in a little tiny positive test charge and imagine what direction would that be forced. It would be forced inward. It would be attracted. Okay? And so that's what you have to imagine when you're asked in a problem to give not only the magnitude of the electric field strength in a region, but its direction. What direction would a positive test charge be forced in that region?